Okay, hi everyone. In this video, we'll be looking at some questions involving how to show a set with an operation is a metric space. So just a quick recap as to the definition of a metric space. So, so X is a non-empty set, and we could define on it a function that goes from X cross X into R is said to be a metric if it satisfies four properties. So we could call it M1. The first one is that, so if for any X, Y, and Z in the space X, we have these properties. The first one is that the distance between any 2 points is non-negative. The second one is that the distance between 2 points is 0 if and only if these 2 points are the same. The third one is that the distance from X to Y should be the same as the distance from Y to X. And the last property is triangle inequality. The distance from X to Y, uh, so we could say, okay, X to Y is less than equal to the distance from X to Z plus the distance from Z to Y. So if your function D satisfies all these four properties, we say that your function D is a metric and the set X is a metric space. So what we'll be doing is looking at examples of some popular metric spaces. So there's actually close relation between two of them. If now if we take as X the set f to the n, where f is your favorite field. So for example, this is just Rn, but it could be any field. And if we take as the metric, so d of xy, so these are now n tuples, then we could define this metric. So let me write it this way. Let's do the general metric. So if I do d sub p of xy, I could define this to be the summation. So what I'm going to do is I'm going to subtract the corresponding components. Then I'm going to raise them to the power of p. I'm going to add that from I goes from 1 to n. So x and y are n tuples. And whatever I get here, I'm going to raise that to the power of 1 over p. Okay, so it turns out that x with this metric, d sub p, is a metric space, right? And I think, so the proof of this one, I believe, is in the course notes. So very similar to this, we have another one, which is, so now if I take as my set X to be the set of all continuous functions on some set. So it could be continuous functions on pretty much any set. But for us, we'll look at continuous functions between the closed and bounded interval a, b, mainly because we want to take the integral of it. So I realize in this definition, I should have told you where p lies. So p lies between, in these two examples, p is going to be between 1 and infinity. Um, if P is infinity, there's a special metric for that. That is the metric generated from the supremum norm. Um, if P is 1, it still works, so we could include 1. So if now the space is the space of continuous function, then we could define a metric that looks very similar to the one in f to the n. So again, we use d sub p, but now you need to remember that if you are in the space of continuous functions, your x and y, those are functions. So the points in this space are functions. So what this metric is, it's the same thing as the one before, except instead of the summation, we're going to do integral. So we're going to take the integral from a to b, and it will be the integral of the function values. So let's say x of t minus y of t. Oops, that should be y of t minus y of t. And then just like before, you take that to the power of p, and then you take the integral of it, and then I should put in like a dt there. And then we take 1 over p. Okay, so it's very similar to the one before, except instead of a summation, because I don't have n tuples anymore, I need to replace that with an integral. So again, x with this metric is a metric space. So we're going to prove this one, the one for continuous functions. Okay, so this is what we're going to prove. Okay, so proving this basically boils down to I need to verify that this metric d sub p, where p is between 1 and infinity, satisfies these 4 properties of a metric space. So whenever we have to basically show that something is a metric, usually M1, M2, and M3, in most cases, they're the easy ones. So usually these are the easy ones. The one that is usually poses some trouble is M4, triangle inequality. And we'll see that triangle inequality for this one, we have to do a bit of work to get to it. In fact, okay, so we can write it here. In fact, it's given a special name. So the triangle inequality in both of these spaces, because it's actually a very important inequality, is given a fancy name. It's called Minkowski inequality. So for the space of Fn, you have a Minkowski inequality, and then you also have the version for it in the space of continuous function. So depending upon what metric space you're in, when you say like Minkowski inequality, then you will know which one of it to use. And the proof of both follow the same steps. So to prove, so right here, the triangle inequality, which is M4, the fourth axiom for a metric, in these spaces is commonly called Minkowski inequality. Let me get his name correct, the spelling. Minkowski, Minkowski's inequality. Okay, so Minkowski's inequality is nothing but it's just the triangle inequality for each of these spaces. It turns out in order to prove Minkowski inequality, so that by itself is it's a bit involved. You have to go through well, you can think of it like three steps. The first one is you need to prove something called Young's inequality. So in the course notes, where it have the proof of triangle inequality for this, if you look at the course notes, you're given a hint, and it say you may assume some relation. We'll look at it in a bit. That relation is called Young's inequality, and there's a proof for that if you want to look it up. Then you need to use that to prove a next one. This is called Holder's inequality. And then once you have Holder's inequality, then you could get to Minkowski's inequality. Okay, so it's actually a bit a bit of work just to get to Minkowski's inequality. So let's see if we could do that. So again, the Minkowski's inequality, it has different versions. Okay, and you might come across different versions of it. So the one we're going to show is the version for this space, right? So we'll be using the integral. So this Minkowski inequality will have an integral in it. But if you ever see a version of it with a summation, then it's the same Minkowski inequality. It's just for the space f to the n or r to the n. And the proof of that one is exactly the same. So the proof of it is the same in both spaces. You just have to do some minor adjustment. What do I mean by that? Instead of using summation, you just use integral. But we're seeing a bit that there's a little trick in it. The trick in both cases um, is the same. So let me see if I can write this down. Um, okay. So here's the setup of it. So we're going to let P be some number strictly between 1 and infinity. So for the case of P equal 1, that case is pretty obvious. So if you go back to our spaces, if you put P equal 1 into it, that just follows from properties of the integral or properties of summation and properties of the modulus when P is equal to 1. So plug P equal to 1 into these metrics, dP, and you will see it's straightforward. The problem is when P is a number bigger than 1. So we look at that case. So when P is strictly between 1 and infinity, we also have a second number, a Q. And this Q is bigger than 1 as well. Q bigger than 1 such that, so the relationship between P and Q is 1 over P plus 1 over Q is equal to 1. When you have two numbers like this is called conjugate exponents. Okay, so these are referred to as conjugate exponents. So for f and g in continuous functions between closed interval a, b, so the first thing we want to prove is we want to show that the integral from a to b of, okay, so instead of f and g is in the notes. Let me stick to x and y. Should I stick? Okay, yeah, let's stick to x and y. Right, so x and y. So remember again, if x and y belong to C of AB, x and y are functions. So x you could call it if you want f, and y if you want you could call it g. But these you need to remember x and y are functions. So the integral of x of t, y of t, the modulus of that, dt, I want to show that this number is less than or equal than if I do the integral from a to b of x of t. I raise that to the power of p, and then I do the pth root of it. multiply by the integral from a to b y of t, then I do the q root of take it to the power of q and then do the q root of it, 1 over q. Okay, so remember the relationship between p and q. Those are conjugate exponents. So this is called, this is Holder's inequality. Right, and if I go back to the previous page, so our aim is to get to Minkowski's, right? And we're asked to prove Holder's. So I have here, you need to start with Young's. So, so in this question, um, proving Young's is a whole, it, actually, if you know the trick, it's straightforward, but it's like a trick in calculus. So for this proof, we're going to assume that we have Young's inequality. So I'm going to assume that I know this. Alpha beta is less than or equal to alpha to the power of p over p plus beta to the power of q over q. Of course, p and q are conjugate exponents. 1 over p plus 1 over q equal 1. I want alpha and beta. Alpha and beta are just real numbers. Okay. So this, yeah, this is Young's inequality. And then of course in functional analysis, you will have to start there. You will have to prove Young's inequality, then Holder's, then Minkowski's. But we'll assume that we know Young's and let's try to prove Holder's first. Okay, so actually if we know Young's, Holder's is pretty straightforward. Throughout this entire thing, because we're lazy and we don't want to keep writing back terms like this. Integral of AB, modulus of something to some power, close bracket to 1 over that power. I don't want to keep writing back these things because these things are going to come up very often. So let me make a definition for that so I don't have to keep writing it back. So I'm going to define, or if you want, let the norm. So I'm calling it a norm, but we haven't proven that. So the P norm of some function x to be exactly what you see here, right? So this term, we're going to define it. Be the integral from a to b modulus x of t to the power of p dt all over 1 on p. Yeah. So the fact that we're writing this thing as a norm should be a hint that this thing is a norm. In fact, it satisfies all the conditions for a norm. If you're in the space of continuous functions, this works out to be a norm. Okay, this is more commonly known as the LP norm. Right? But you will have to show that this is a norm. The fact that this quantity, this collection of integrals, p root, 1 over p, the fact that that actually works out to be a norm doesn't matter for this proof. Okay, all we want to, the whole reason why we're defining it to be written as a norm is just to make our life easier, right? We're not going to use any property that it's a norm in this proof. Okay, so we're just going to define it like that and leave it that way. So therefore, required to prove. So let me rewrite now Holder's inequality using this new definition. So I need to prove that the integral from a to b of x of t, y of t, modulus of that, dt, is less than or equal. So now instead of writing, that integral of a to b modulus x to the power of p and all that stuff, that is just simply the norm of the norm of x by the norm of y. You see, it's a lot easier to write it now, right? And now I need to remember which subscript to use. So the one for the x, that's p, okay, because we're taking it to the p power, and the one for the y, we're taking it to the q power. So I'm making reference with these numbers here. So I use norm xp. And for this one, it's q. So I use norm yq. Right, so one is p, one is q. So that is my target. So that there is Holder's inequality, but written in a nicer way. And I'm assuming Young's inequality. So the trick is, so the proof. So first we just need to verify what happens if any one of these guys are zero. So if the norm of x, actually usually we don't even put x of t, we just put norm of x. Anyway, I'll include the t. What I'm saying is that usually if you ever see this in textbooks, they don't even put the t, they just put norm of x. Okay, but I'll put the t in, x of t. So if this, or the one with the y, is zero, then, so let's just look at what this guy is. So if this term happens to be equal to zero, what can I say about the function x? Okay, so let's just take, for example, this thing, p. If this thing happens to be zero, so let's write back out what it is. So it's integral from a to b. You don't have to do this step, but I just want to write it because you should see it at least once in your life. 1 over p. If this term happens to be zero, it's the same thing for y. But if this term happens to be zero, now, well, I'm taking the p root of it. So I could take everything to the power of p. In other words, this 1 over p, I could get rid of that. So that means that the integral from a to b, this term must be zero. And it actually goes both ways. So now, if the integral of something from a to b is equal to zero, so now we'll see in a bit that this might pose a bit of problems. But x is a continuous function. And what I'm integrating here is never negative because it's the modulus of x. Okay, so you can figure out about the to the power of p. That's not so important now. Then this means that the integrand must be zero. Okay, that's the only way that can happen. If the function is continuous. If the function is not continuous, this wouldn't happen, right? That's why you need to be in the space of continuous functions. Okay, and if the modulus of some number to the power of p is zero, so from here, it's straightforward. Then that means that this term inside has to be zero, and it has to be zero for all t in AB. Okay, so I should have probably have that written all the way. Okay. For all t in AB. Okay, so you get the idea. So that's the same thing as x being the zero function. So x is the zero function. Sometimes they use theta to denote it. So all of this is just to say, if it so happens that one of these norms, or even both of them, turn out to be zero, then the term in here is the zero function or is identically zero. Okay, so if that is the case, then if we look at what we have to prove, required to prove this, if let's just say x is zero, right? So let's say the norm of x happens to be zero, then the right-hand side is zero, and this term is zero. So the left-hand side is zero. In other words, if one of these or both of them turn out to be zero, you have Holder's inequality. So that's trivial. Then Holder's inequality holds, right? The problem is what happens if they are not zero. So now consider uh, so the p norm of x and the q norm of y are non-zero. Okay, because if they are zero, it works. Okay, so if they are non-zero, go to any page. So yeah, the the proof of this thing is actually a bit long. You could shorten it. Actually, some textbooks they might do the proof in maybe like one page or something, but they are skipping a lot of things. So it looks short, but they're skipping a lot of stuff. So if now those norms are non-zero, then we could let, so now I'm going to let alpha be this number. So if the norm was zero, I couldn't write it here. Okay, so because the norm is not zero, I could divide by it. So I'm going to let that equal to alpha, and I'm going to let this one equal to beta. This was Q. Okay. So if you just look at these two quantities, it's obvious that both alpha and beta are strictly bigger than zero. And this is exactly what I need for Young's inequality. So apply Young's inequality, which says that alpha beta is less than or equal to alpha to the power of p all over p plus beta to the power of q all over q, right? So now we're just going to sub in. So again, this is Young's inequality. We're just going to sub in alpha and beta. So alpha times beta, so that gives modulus divided by norm. So think of how much writing you would have had to do if you didn't define the norm or the norm symbol of x and y to be those integrals. Then you will have to write out all those terms. The integral from a to b of the modulus of x to the power of p, all raised to the power of 1 over p, and so on. You'll have to write out all of that. So it will get, let's see. Yeah, so on this side, so I'm raising alpha to the power of p. So that would be modulus here to the power of p all over p. So p is just some number. Norm. So this is the p norm, but I'm raising it to the power of p. Plus y q by the norm of y q, and I raise this guy to the power of q. Okay, so from here, very easy. You just integrate both sides from a to b. So now integrate both sides from a to b. And what you need to remember is that the norm, so these these things are numbers, right? These are numbers, fixed numbers, because they have already been integrated, right? If you look at what the definition is, this is given by a definite integral, and a definite integral, when you integrate something from a to b, you get a number. So these things are numbers. So if I'm going to integrate both sides now from a to b, you know that you could pull numbers out. Okay, so we could pull those numbers out. So I can write this as 1 over the norm of x. So now I'm going to drop the x of t. Okay, so I'm just going to drop the x of t and the y of t. The integral from a to b, because these things are just numbers. The modulus, so now I need to include it here, dt. Okay, and this is less than or equal. So again, p is some number and the norm is some number. So I could pull that out of the integral, or said another way, I just need to integrate the numerator. So let's write it like this. So integral from a to b of x of t, p. Okay, and then I divide it by this number. So norm e to the power of p plus integral a to b. There's a dt in here. I of t dt. There's a q here divided by this number. Okay, that's the same thing as pulling the number to the front of the integral. It's the same thing as multiplying by 1 over that number. Q, Q. All right, and now we just need to observe, for example, what is this? The integral from a to b of the modulus of x to the power of p dt. This part here is just the norm of x to the power of p. Right? So what I have in that numerator is just this term. There's no 1 over p. So it's just this term. Okay, so this thing is equal. So in the numerator, that's the norm of x, the p norm of x to the power of p, divided by p by this number. Right, and of course, those terms will cancel. Plus, this one, well, that's just the q norm of y to the power of q, divided by q norm of y, q, q. And those things cancel. We got 1 over p plus 1 over q, but we know p and q are conjugate exponents. So 1 over p plus 1 over q is 1, right? So this thing is 1. And what do I have on the left-hand side? On the left-hand side, I have this. So this number in front of the integral, that number is, of course, always positive, right? This number here is always positive. So I can multiply through by that number and not change that inequality sign. So this implies with the integral from a to b of the modulus of x, modulus of y, dt is less than or equal, so I multiply through by that, and I get the norm of x, p, norm of y, q, right? So that's what we have to prove. That's Holder's inequality. So straightforward, if you know Young's, if you know Young's inequality. Okay, so now that we have Holder's inequality, we could prove now Minkowski's inequality. Okay, so let me write Minkowski. Okay, so this is part B. Okay, so part B, Minkowski's, which is what we wanted. So Minkowski's inequality is triangle inequality. It essentially is triangle inequality. Um, so I want to show that the integral from A to B of x of t plus y of t uh, to the power of p dt, and then I raise that to the power of 1 over p. It is less than or equal to the integral of the first one plus the integral of the second one. Okay, so this is Minkowski's inequality. Right, it's essentially triangle inequality with respect to the p norm. So why do I keep saying that? So again, what did we define as the p norm? This thing, this thing, right? So we define this to be a p norm. Again, we don't need to know that this is actually a norm. All we need to know is that this symbol on the left represents, you take the integral of whatever function you have, you take the modulus, raise it to the power of p, integrate that, and whatever answer you get, you take the pth root of it. That's all we need to know. So I'm going to rewrite Minkowski's inequality in terms of that symbol, in terms of the norm symbol. And then you'll see why I keep saying this is triangle inequality. So if I rewrite that in terms of that symbol, the left-hand side just turns into the norm of x plus y, the p norm, is less than or equal to the norm of x, this thing here. This is the norm of x, the p norm of x, plus the norm y, right? And of course, this is triangle inequality. So this is what I need to try to prove. Of course, x and y are of course x and y are continuous functions, maybe. Okay, and according to our little roadmap here, I need to use Holder's inequality somewhere to prove that. Okay, so yeah, so what's the trick? So the trick is the left-hand side, we're going to write that to the power of p. Okay, so this is our starting point. I'm going to take the whatever I have on the left-hand side there and write that and raise that to the power of p. So um, so we could work with it like in terms of this norm symbol, but to kind of show exactly what's going on, maybe it will be clearer if we go back to what this norm symbol means. So yeah, maybe we could go back to the integral to writing the integral sign. So we see exactly what's going on because I'm going to separate out this term in a bit. Okay. So that's what happens when I take the norm to the power of p. I basically get rid, because before you have this thing raised to 1 over p, but because I am raising it to the power of p over here, this part goes away. Okay, so that part there goes away. Um, so what I'm going to do, so the trick is the term that you are integrating, we're going to pull apart that term. So no need to cram it off. All you need to know is remember this trick. So I'm going to pull out norm of x of t, sorry, modulus of x of t. I'm going to pull that out. I get modulus of x of t plus y of t. And if I want it to be the power of p, then there should be p minus 1 dt. That's the trick right there. Now I'm going to apply triangle inequality to this term. Okay? Because this is just the regular modular. So apply triangle inequality to that term. So it's less than or equal. Now the integral from a to b, and it will be modulus of x of t plus modulus of y of t. Okay. So what I did there was I just broke up this term into the sum of these two terms. That's triangle inequality. And of course, I need to multiply by this guy. So multiply that by this term. X of t plus y of t, and it's raised to the power of p minus 1, and that's dt. Yeah, so from here, I could break up now this integral into two integrals now. So let's split this apart. So AB x of t by this term, which is x of t plus y of t p minus 1 dt. Okay, plus the integral of the second term. That's y of t p minus 1 dt. Okay, so I just multiply this by this, multiply this by this. You get two terms inside the integrand, and then break up the integral into the sum of these two terms. So one term, two terms. Now we're going to hit both terms with Holder's inequality. Let's see if I copy and paste this. Yeah. Okay. So that term, and I need this. Right. Okay, so it's not quite equal, it's less than or equal. Yes, correct. Yes, less than or equal. Okay, so that's what I have from the previous page. Okay, so I'm going to use Holder's inequality 2 times. So actually, since it's the first time you all might be seeing this, it might be easier to do each part separate. Okay, so I'm just going to take this first part and let's look at this first part. The second part is exactly the same, right? The second part is exactly the same. So let's just take that this first integral and work with it. Of course, you don't have to go through all this stuff. You can write all of this straight, like continue the work in, but this is just what's that easy, right? If you've never seen it before, it's good to work it out separately so you know where all this stuff is coming from. Okay, so Holder's inequality, I copy and paste that too. Yes. So this is Holder's inequality. But I want to replace the x and the y in Holder's inequality into something different because it's different terms. Because I don't want you to think that the x and the y are the same as the x and the y in what I have above. So instead of x and y, let me just replace those letters by, let's say, f and g. F and g. Okay, so it's same Holder's inequality. I just mainly turn this up. Yes, f of t plus f of t multiplied. F of t multiplied by g of t. Yeah, so that's what we proved there. So uh, the trick is, yeah, so the trick is, so the second trick in the question, this is your f, and this entire term here is your g. Okay, actually, so you can see it better. You of course know that the modulus of AB is equal to the modulus of A multiplied by the modulus of B, right? So what I have here, I could break that up into, instead of the modulus of F, G, I could break that up into the modulus of F by the modulus of G. That might make it easier to see. Okay, so I'm just breaking that up. So it's the same Holder's inequality, by the way. Same Holder's inequality. I'm just writing the modulus, I'm just breaking it apart. So F, so we could see better what's going on. Okay, so that guy is the F and that one is the G. So let's apply Holder's inequality. Okay, so from Holder's inequality, this means that the integral from A to B of this term P minus 1, so that's the left-hand side, is, so now I use Holder's inequality. So this is telling me this term is less than or equal, so it's the integral from A to B of f of t. What was f of t? F of t was my x. So modulus of x of t to the power of p dt, all raised to the power of 1 over p. Okay, and I'm going to multiply that. So I'm going to multiply that by what's on this line. So that's the integral from a to b of g of t. So now g of t is this entire term. It's modulus of x of t plus y of t. So that's my g. Of course, it's p to the minus 1. So this is my g. And according to Holder's, I need to raise this to the power of q. So I need to take this to the power of q. Then I do dt, and then I take the 1 over q root of it. Right? So I know what you're thinking. Okay, this is starting to look like a mess, but it will simplify it out. The first term, the first thing to notice is that this term here, this is just the norm of x. Okay, that term there, that's just the norm, the peak norm of x. Right? This second term now, okay, let's write it back. Right, integral from a to b. So I could do x of t plus y of t. So that using my rules of indices, that is q into p minus 1 dt. Then I take the q root of that, 1 over q. Okay, so now, what is it? Recall. that 1 over p plus 1 over q is equal to 1. So from that, I could write p over q, q plus p equal 1. Then cross multiply, and I get q plus p equal pq. So which one do I want? So therefore, P is equal to PQ, yeah, minus Q, yeah. So P is Q into P minus 1. This term here is P, right? So that term there is just P. So that thing is equal to the norm of xp, integral from a to b, x of t plus y of t. So that number there, we will tell that number there is just p. Dt of 1 over q. So the next trick is, oh, okay, yeah. So the next trick is, so just by looking at it and trying to figure out what you want to get, it will tell you like what you need. So the problem is, this exponent here is a p. This one here is 1 over q. If instead this was 1 over p, if this q was a p, then this will be, we can write this as a p norm, right? It would just be the p norm of x plus y. So what I could do is, I'll do it here. What I could do is, I could, so it's 1 over q I have. I'll put p, oh, let me write it like this. I'll put 1 over p, and I need to get 1 over q. So it's, use that next type of bracket now. P over q, right? That way, when you multiply it, you'll get 1 over q. And this term is just a norm. Okay, so that's equal to the norm of x, p, and this thing is just the norm of x plus y, the p norm, but it's being raised to the power of p over q. Okay, and p over q, that's equal to our next number. So now we have to work out what that number is. So again, we go back to 1 over p plus 1 over q is equal to 1. P over q, so let me multiply through by p. So p over p plus p over q is equal to p. So p over q, which is what I want to figure out, is p minus 1. Okay, so this term up here is p minus 1. Okay, so that is equal to norm xp, norm x plus y, p to the power of p minus 1. Okay, and now we're almost finished. We just have to put everything together. So what was on the left hand side? This is on the left hand side. So that's what we were working with. And we just showed that that is equal or less than. That's not less than or equal to this number. Still. So this is what we just went through, all that trouble for. So therefore, this thing is what we showed. That thing was less than equal to this. And maybe I should number these equations. Let's call this guy 1, right? So what we just did was we have a bound for one of these. Well, not a bound, but a substitution for that. Okay. So now I could draw here. So what we just did was we just worked out this part, right? This part is this guy up here, right? And it's less than equal to this thing. And if you look at this second part, we're not going to do this calculation again because it's the same thing, except instead of x, you have a y. So it's the same thing. Okay? So I'm just going to sub all of this into 1. So that's where it came from. So I could just say, uh, let's call this 2. So sub 2 into 1 gives, uh, so that was the left-hand side, and it's less than or equal. So the first term was this guy, and it was plus, was it plus or multiply? Plus. It's plus that second term. So it's plus, and the only thing that's different in that second term is this first part here was a y, became a y. The second norm is exactly the same. Okay. And now all I do is, so we're basically done. You just need to divide through by this number. So divide through by norm of x plus y to the power of p minus 1. So that gives x plus y, p to the power of p. So divide through by this number. And of course, that number is not never negative, so I don't have to worry about the sign changing. Xp plus yp. Right, so this thing just gives normal x plus y. So you use your rule of indices. So p minus p plus 1 is 1. All right, so finally that is Minkowski's inequality. Right, where is it? Minkowski's inequality. Okay, that's what we needed to prove. So that's the proof. Yeah. So that's it for the in terms of it being a norm, but how do we prove it in the sense of a metric? Right? So we prove on Minkowski's inequality, and I claim that in order to show, so the original question was, in order to show that this space under this metric, so it's a metric, was a metric space. So it's easy to check that this metric satisfies the first three properties, right? So I'll leave you to check that, these first three properties. What we're going to do now, now that we've proven Minkowski's inequality, we're going to show it satisfies this one now. Okay, so that's our target. Okay, so almost there. Let me steal this. Okay, so this is the metric now. That's the metric. Doing M4 triangle inequality for this metric. Okay, so um, so we could start with dp x comma y. Again, let's just write back this. Yes, that's integral from e to b x of t minus y of t to raise to the power of p dt to the pth root. And now what I just write back here, this thing looks familiar because this is just, well, that's this part here. That's just this. But instead of a plus sign, you have a minus sign. Okay. So that is just the pth norm of x minus y. And what I'm going to do is the oldest trick in the book. You're going to minus z plus z. So again, z is some in all of this. X, y, and z are continuous functions on UB. So add z minus z minus y p. Okay, and what we're going to do there is now apply Minkowski's inequality. So Minkowski's inequality, remember, it's just triangle inequality. It says that if you have this p norm, again, we don't know it's a norm, but if you have this p norm, it satisfies the triangle inequality. So instead of x, I have x minus z, and instead of y, I have z minus y or y minus z. If you pull out a minus sign, it doesn't matter. So apply Minkowski's inequality. X minus z p plus we could write z minus y p by Minkowski's. Okay, by Minkowski's inequality. And okay, well, from here you can see it, but if that's right. So let's convert back to the integrals. So what does this x minus z means in terms of p? Okay, let's go on this minus sign first. So I could switch this order instead of z minus y, that's the same thing as y minus z. And now let's write it back in terms of integrals. So this is just the integral from a to b of the modulus of x of t minus z of t, p raised to the power of 1 over p, plus the integral from a to b y of t minus z of t, p to the power of 1 over p. Right, and if you check the definition of the metric, the p metric we were working with, that's just dpxz and dpzy or yz. It's just dpxz plus dp zy or yz, doesn't matter. Okay, so triangle inequality. All right, so that's how you show. So Therefore, continuous functions, closed interval a, b, with this p metric is a metric space. Okay, of course, this is just the proof of M4, triangle inequality. You then need to prove M1, M2, M3, but that's not too bad. Okay, so video is getting pretty long, so I'll stop it here. We look at the next example.